But when you look at those tools, they can tell you an awful lot of information about what the problem is that's potentially affecting the customer. And if you understand how the images are constructed and how to read them, it can be very informational and efficient in getting you to the primary root cause. So we'll get into some of those. But first things first, just some of the basics on what the signals look like. In these full band captures, we have our 6 megahertz single carrier QAMs, but then right next to it is a 96 megahertz OFDM block of channel or haystacks. And the tops of it look a little bit different because there are some timing carriers inside the OFDM that kind of sit on top and make the top look a little jagged. Then you'll have other carriers like CW or constant wave carriers that are analog tones, sometimes out there for ALCs or for leakage or for other things. Now there are guard bands, very, very small ones in between the single carrier QAMs, the 6 megahertz carrier QAMs, and then oftentimes there'll be bigger guard bands in between different channel types, like this OFDM next to the single carrier QAM, there's a guard band there. And then other times, depending on your channel load and how many DOCSIS or linear video channels you may have and the band pass of your system, you'll have some vacant spectrum where you'll have room to put more channels later, but maybe right now you just don't need them. And so you can have different sizes of vacant spectrum, and being able to understand that can be useful in a couple of ways. Oftentimes, if there's ingress, and we'll talk more about that later, you can see some of those carriers in that vacant spectrum, because the modem, if there's ingress in the system on the downstream, it'll be transmitted to your devices, and it'll actually show up as energy on that device. And so it'll be represented, even where there's not a channel, as just noise or energy in that spectrum. So vacant spectrum can actually be pretty useful too. So here's an instance where vacant spectrum is actually pretty interesting. The other thing that we need to consider is the type of device that we're getting the information from. As we move on from the basic sub-split systems into mid-split and high split and beyond, if that's the direction of your company, our customer premise equipment will also need to be sub-split or mid-split or high split in order to activate or use that spectrum in both the upstream and the downstream. So we have two different devices here. The one on the top is a sub-split device. The one on the bottom is a mid-split device. Now, these could be on the same network, but the way that the signal on the downstream is represented is going to be very different. This device, the sub-split device, has a diplex that rejects below 42 megahertz or 45 megahertz, depending on the band edge. Now, the other device has an 85 megahertz diplex, so it will reject anything below that. However, this particular type of device has something called UDA, which stands for Upstream Diagnostic Analyzer, and in the future, the working group is working on the math to actually represent the return portion of the spectrum inside that house from that device. Now, how cool is that? Where you could actually use the modems in the house or the customer premise equipment as a spectrum analyzer to look for return noise. Now, right now, this just looks like an elevated noise floor. Some people may think that this is OFDMA return energy. It's actually not. It's the noise floor of the UDA spectrum analyzer. Okay, so it's important to understand what devices you have deployed into your system, what chipsets they have, whether they're Intel or Broadcom or something else, because all of those chipsets behave a little differently, and we'll talk more about that. Now, on the top one, you can see that there is a diplexer rejection below 45 megahertz, so you can't see anything that's happening in that portion of the spectrum from this device. Again, this is most likely a modem, and if you think about a modem, its primary job is to modulate and demodulate signals, right? It's to transfer information back and forth. However, this is kind of a bonus. The ability to look at these P&M MIBs or data points and then reconstruct other things or develop other tools outside of just the ability to transmit information up and down. It's kind of like your car. Its primary job is to get you from point A to point B, right? That requires an engine, brakes, etc. But your car has other features. It may have, an onboard navigation system, have onboard Wi-Fi. Those things aren't the primary function, but they're super useful, right? To help you navigate. There's all sorts of other systems in your car, like your tire pressure warning or your onboard diagnostics that may tell you when you need an oil change, right? Those aren't the primary function, but they're informational about the overall system that is your car. These modems are the same way. They have these other features that can give you information about the performance of the system as well as transmit packets back and forth. So that's almost an afterthought anymore, because you just sort of assume you hook it up, you've got RF upstream and downstream, you're gonna have internet. But the reality is there's so much more capability from these devices to tell you what's going on, not only inside the premise, but in the system at large. Now, Brady did a great job of talking about how the equalizer taps and coefficients in the devices on the upstream transmit side can tell you about localization of impairments at a very specific frequency in the upstream path. Likewise, these full band capture devices can tell you the same thing in the downstream, but in some cases with some more evidence of what the actual problem is. Now, on the upstream, it's really looking for cavities or reflective cavities or nonlinearities that result in group delay and impairments in the in-channel that affect the in-channel frequency response. When we think about the upstream ICFR, it's sometimes difficult to get your head around because we're talking about tiny little 3.2, 6.4 megahertz chunks of spectrum. But think about it in the downstream. When we used to sweep long amplifier cascades and we looked at our peak to valley to determine the overall frequency response and linearity of the cable and the amplifiers. Well, the ICFR is the exact same thing, only in the upstream, and it's in much smaller chunks. So back to the downstream, the full band capture capability of these devices can tell us, in this instance, I would say there's a bunch of noise coming from this house, because in this portion of the spectrum,
did it just freeze up for everybody?
Single carrier QAMs here and here, but there are no active channels. You can see this, you can also see evidence of the downstream. And then in this area, you see this large elevation of noise. Now you think, well, it's not in the return path. Well, that's because the device's diplex filter is cutting that off. That portion of the device is actually used to transmit information upstream, so it doesn't represent any of this energy in the downstream. But you can extrapolate that this elevation inside the premise on the downstream at this device likely includes the sub portion of the spectrum too. So the energy is there, the diplex is just cutting it off so you can't see it in the downstream. Now this device you can also see has some FM ingress here as well. So that's indication that there's a shielding integrity problem in the house or out in the plant, and there's FM energy getting into the cable plant being transmitted all the way to this device. So just a couple of nuances on how to understand what device it is, what the diplex cutoff of that device is, and then how different devices react to representation of the full band capture. In Brady's presentation, he mentioned there's a long string of hexadecimal code, right, that was in there, and that's the mathematical representation of this data. Well, these devices have something similar, and then our systems take that information and basically recreate this spectrum on the downstream. But sometimes there's other information that comes from the device in that code that gets misrepresented visually. So like these artificial noise spurs. You might be tempted to take a good spectrum analyzer out there and look at the downstream and say, where is this electrical interference noise coming from? Well, it's not there, it's not real. It's just a representation from that chipset in our intelligence tools and how we decode it. Now, this other one is a switchable diplex. So we have some devices out there that are capable of being operated in both the sub-split or the mid-split mode, right? Potentially even high split in the future. And there's an artifact that gets created by that switchable diplex right at that band edge. So just understand your customer premise equipment, the chipsets that are in them, and how they can represent differently in the visualization tools that you have will help you take some of the noise out of the equation, so that when you get to other impairments, that you can easily identify what the impairment is, what some of the likely causes are, and eliminate some of the red herrings or the artifacts that aren't actually present. Now, the other thing we need to know is there's a power relationship between how the DOCSIS devices themselves measure power on both the downstream and the upstream side in composite power across a portion of the spectrum versus the mathematical representation that we see on these spectrum analyzer tools. So for instance, we're looking at the same device in two different ways. This is a Comcast tool called Scout, and it's telling us that the downstream receive power of that device is right around 0, plus or minus a half. Now, when we look at the visual representation of that tool, it actually shows on the vertical axis that the power is -17. So what's the actual receive power at the device? Is it 0 or is it -17? It's actually 0. So when you're looking at some of these screenshots, what you need to do is to look at the amplitude or the vertical reference level and then add 17 to it to get the actual power at the device. Now, some tools could be slightly different. It's a logarithmic equation that determines the delta there. Some other tools are 18, some could be 15, but most of them are somewhere around 17 dB delta. Okay, so let's start talking about the different types of impairments that tools like this can help us define. The first one we'll talk about is an adjacent channel alignment. So there are several different examples of this. You can see here in the low portion of the spectrum here, right around 107 megahertz, there's a channel that's just sticking out. A lot of times we see that with local insertions. You have an apartment complex or an MDU, and they want to look at their parking lot or their front door cameras or whatever. So they'll have a digital insertion with a modulated channel from their cameras and then insert it into our lineup. If that power isn't matched to the insertion point power at the combiner, then you'll have that adjacent channel alignment. So that's a quick indicator that, hey, if all of the modems in this apartment complex or MDU have this one channel sticking out, but the neighbors outside of there don't, well, it's a local insertion issue. Now, other times you'll see things like this. So the bottom half of the spectrum is the linear broadcast or video channels, and then you get into your DOCSIS channels or your narrowcast channels, and that's typically a product of combining in the head end. So if you see that in the house, there's typically nothing you can do to fix that in the house, right, or in an amplifier. You can't go out and adjust your narrowcast versus your broadcast. That's typically a head end function. Very similar with these other two examples. We'll have a portion of the spectrum. It could be 4 channels, it could be 8 channels, but then adjacent to that, there's a significant difference in the power levels. In a lot of cases, that's in the head end. Okay, standing waves. Now these are what we call simple or periodic standing waves caused by impedance mismatches. So just like Brady talked about those impedance mismatches and the reflection of energy back and forth inside of a reflective cavity. The similar thing happens in the downstream as happens in the upstream. However, it's represented differently in the downstream because we have much more spectrum that seems connected than in the upstream, where it's smaller channel frequency responses that are disconnected. Now, there is a formula where you can take and measure, and I bring this up because I mentioned the deck that John Downey shared with me in 1990 something. In that deck was the formula for how to measure the peak-to-peak distance in megahertz and determine how big the reflective cavity was. So it was a way of calculating cavity size, reflective cavity size, before we had the intelligence tools to do it. So you just had to measure the peak-to-peak of your standing wave at a point and then do the math at the difference in frequency from the peak-to-peak or null to null, and you could determine how far you were from the reflection. Looks like somebody's talking in chat here. Let's see who that was. Oh, thank you, John. The reference power is based on the resolution bandwidth, John says, going back to the previous slides. And to have a 17 dB correction factor, the cable must be using a resolution bandwidth of 100 kilohertz. Thank you, John. So